Hey, what's going on, everybody? In this video, what I'd like to go over is what I've termed, I guess we could call it the rule of three. Now, this is not something, as far as I know, that you'll find in any textbook or any of the literature. It's just something that I sat down one time in a recent tutoring session and realized, oh, this might be something really simple to remember. The rule of three, and it has to do with resonance structures. So rather than going on the details that I've been doing before, I'm just going to give you a couple of structures that we can kind of look at and we can figure out how this applies. So we'll leave that one. Let's go. Try that one. Trying to think of some other things we can do here. What if we, let's do this. Actually, this might be okay. Okay. Rule of three. Let's move these out of the way. We'll start with this one first. We can always come back to these. All right. Rule of three, what you're looking for is when you have a charge or even a lone pair, I guess really to kind of give you another example, it doesn't have to be all charged. It could also be, I'll just draw it up here so visually we can see it. It could be a plus. It doesn't necessarily have to be a plus as well. We could actually have a completely neutral molecule. So let's say H, and whoops, that's neutral, lone pair. So we can actually I guess, go through all of these because once we see the point or what's going on with it, you'll probably see it. All right, so rule of three. What that means is you're looking for your point where you're going to do your resonance. A lot of times it's going to be charge in your class. You're looking for the positive or negative charge. You're going to start at that carbon. You can do it this way or you can go the other way. And what you want to do is you want to count 3 atoms. So in this case, we're going to have 1, 2, 3. When you get to the third position, that should encompass or be your double bond. The other thing you want is you want to make sure that whatever direction you're going, that your 2 position also contains a double bond. I'm going to show you that in a minute, but this is basically to show you. If you have the 1, 2, 3 system, meaning that your charge is on the 1 or the 3, you can do it the other way if you want. 1, 2, 3. That whatever number your charge is on, 3 or 1, that then your double bond is on your 1 or your 3. So if we look at this one, then that means that we just take our negative charge, we push that down, we push that up, and that'll give us O minus, like that. What the 1, 3 is telling you is that your charge should always be on, if you count your 1, 2, 3, on a 1 or a 3 position at all times. So that's what that looks like. So when I talked about it has to be in a specific position, what does that mean when I said the 1 or the 3? So if we look at this, if we count this, we've got 1, 2, 3. Now I said make sure your 1 or 3 has a double bond. You see how in this case your double bond is not contained within your 1, 2, 3 system. So you want to make sure your double bond, if we were to switch this, what would it look like? Keep the same number of carbon chain, but what would have to happen is it would have to be, in this case, 1, 2, 3. So your double bond has to be contained within your 1, 2, 3 system. As long as it is, then resonance will work. So this one, we can see that when we push that down, it doesn't work because we're not touching the double bonds. That's another way you can think about it is when you take your charge and you bring that down, when you form your bond, it should touch one of the sides of the double bond. So therefore, it's like you're pushing it. You push that in, you can push that out. So that fulfills our 1, 3 system. If you don't want to go through there and your professor says how many resonance structures you can have, you can always check yourself. So let's just jump in. We don't need to do that. That's the same. It just happens to be, well, I guess I can point this out. The reason I've been using negatives is because you always take your negative and you move it. You're moving your negative in a specific direction. So it's like your negative is pushing in on the double bond and pushing it out. With the positive charge, you're always going to have things getting pulled into it. So think of like positive attracts and negative kind of pushes. So with a positive, it's attracting. So what happens here is you don't go positive in because you don't have any electrons to work with. Your double bond is going to move towards your positive. So in this case, I'll just do it quickly. Is going to do your positive. So we notice with our negative, you start with a negative and you're pushing it in a direction, your positive actually goes in the opposite direction. So remember, negative you're going to push, positive is going to go in that. So we can get rid of that. So if we have a more lengthy one, something like this, to do your 1, 3 system, this is why I always suggest start with your negative or positive charge and start counting, have that your 1 position, because when you have a long system like this, it's very easy. If you go 1, 2, 3, that's going to be 1 resonance structure. So we started on the 1, we go to the 3. So we have a charge there. Anytime you get to a 3, that's a charge. So 1, 2, 3 is a charge there. That's your new number 1. And you go 1, 2, 3. So that shows you that in this case there's going to be 3 resonance structures, just to prove to you, because I did that kind of quick. 2, 4, 6, 7, 2, 4. Make sure. So if we look at this, we would move our negative down, that up there. So that's going to give us a double. Now that's a minus. Our double bond is still intact there. And then if we did the same thing again, we would move this down. We've got 1, 2, 3. That's going to push out there. I know I'm doing this messy, but most of you probably had it by the first time, but I just wanted to visually show you as well. So that's going to give us there, and then we have our minus out there. So you can see in this case that we just counted 1, 2, 3, 1, 1, 2, 3, and then we went 1, 2, 3. We figured out what our positions were, so we've got 1 resonance structure there, 1 there, and 1 there. Okay, so that's just to show you the 1, 2, 3 rule. Now what happens if it's not charged? It's exactly the same, doesn't matter. Now in this case, what you're going to be looking for, like I've talked about in other videos, is if you in some cases you're going to have atoms that have lone pairs on them that aren't charged. So in this case, we want 5 electrons around nitrogen. We have 5 electrons around that. So in this case, if we have a lone pair, we can start moving that around. So just like we did before with our charge, we can think about a set of electrons, we can move them. So these can go down here. We can push those out like that. And then what that's going to do, whoops, is give us a double bond here. Now we've seen when we push electrons down and push out, we get a minus. When you have a neutral structure and you do resonance structures, you're always going to generate both charges. You're going to generate the negative and you're going to generate the positive. The easy way to think about this is your negative is always going to be at the end of all of your arrows. So in this case, we have our lone pair. We're pushing it out. At the end of where the arrow winds up, that's where your negative is going to be. Where you started, that's going to be the positive. Doesn't matter how long your chain is. If I wanted to even switch this, I could do an oxygen. Make sure I get enough on here. I could do the same thing. So I take this. We've got our 1, 2, 3. So 1, 2, 3, 1, 2, 3. So it's all connected. So I can push these down there. I can push that up there. And then rather than stopping, I'm going to go all the way out. Well, we'll do each intermediate one. So we already saw that one. So our first resonance structure is going to give us a double bond there. We still have a set of lone pairs. So now we're going to have a minus there. We said that the charge goes in the direction of pushing, so that's a minus. What we're left over is with a plus. And if you just look at this, we can see that for oxygen to be neutral, we need a total of 6 electrons. So we have 1, 2, 3, 4 from the lone pairs. Each bond contributes 1 electron, so 5, 6. Whereas in this one, we have 1, 2, 3, only 5 electrons. We need 6, so that's 1 less electron, which is we've taken away 1 minus. That's a plus. And there's a minus. We still have that double bond there, so we could also push this out in like that. So that would be here, and now we have a minus there, and a plus